So without further ado, I'll present, I can never get your name right, Jeong. I present Jeong with Fighting One-Day Exploits.
Yeah, thank you. Yeah, today I will present about one-day exploits. Yeah, the first one, the introduction, the problem. Actually, security patches are usually meant for fix problems like the latest Microsoft out-of-band patches. They are like used for like fixing security problems. But sometimes just releasing security patches implies something like a new kind of threat, and we call that like a one-day exploits. Actually, many of you already know about the zero-day exploits. And zero-day exploits is before the patch is coming out. And one-day exploit is just after 1 day, within 1 day, like hackers or reverse engineers can make exploits that is exploiting that exact problem that the patch is patching. And this one-day exploit is especially useful for like Microsoft binaries. I tried for other like Sun or Adobe binaries, but they are now releasing the patches like regularly. But Microsoft is like releasing it like every patch Tuesday, like every month. So they are only changing some small bits of the binaries, so you can like find it very easily. So let me check. So this talk is about like making one-day exploit more like difficult to exploit, like make it take more days, like 1 week or 2 weeks to analyze the patches so that the end users can on time they can install patches during the time or something. So we are going to release some very early form of a POC code called Hondon. Actually, it means in Korean means chaos. So it will make the binary like a little bit chaotic and make the binary diffing a little bit difficult. Oh, this one, yeah. So we are going to show the demo first. Actually, usually all the presentation shows the demo at the last minute or something. But I'm going to show the demo first so that you can grab what binary diffing is. Actually, the Hondon demo will be at the last part of the presentation, but before that, you must get the idea what binary diffing is like. So I will show that. I'm going to use MS. Let me check. MS 08000671. So if you look into this, there is a batch script that is doing the binary diffing in command line. So I will show the contents of the file. Yeah, it just looks like this. And here, dark green to c.exe, this one is the program that is doing the diffing. And after options F, and you put like old binary and new binary, and after then you put like the output file. So I will run this script here. It's running, you can see the argument here. And actually it's running in the background the ida.exe to run to send the disassembly information to the Darangrim to c.exe. And it takes a while to like diffing the thing, like 30 seconds to 1 minute. So save the time. Actually, I made a copy here, so maybe you can just open that. Yeah, here you go. You can just sort by the match rate here. Match rate. Actually, the 0% means that the code block is not identified or something because either disassembler is not like can disassemble whole like completely. They can like sometimes think data is code or something. So it happens a lot. So. Looks like you go down there. There's a lot actually. Go 100% means that two functions matched. So go up. That's too many actually. Let me find it. Yeah, here. Actually, you can. This is the first meaningful 3 results here. They don't have a 100% match here, so you can look into just 3 of these functions. And maybe we can look into this more first. This one, if you look into this, looks like meaningless, like some error in IDA. Looks like they failed to recognize data, looks like data. So maybe you can look into this one first, later. And you sort by the match rate column here. You can see that one block has like 89 or something. So the block has been modified. So if you see here, but if you look into this, looks like they only changed some kind of calling convention, not a serious modification or something. So maybe you can just ignore this. And the first one actually is meaningful. Like if you look into this, the red blocks means that there is no matching block in the other side. It means that they added new code, and if it's here, it means that they took out the red blocks. And if red blocks here, they put new code here. And the yellow blocks means the code is, the block, basic block is modified. So looks like this function has go through a lot of modification. So you just need to like open up IDA and just go through what is modified there. So it's not the binary default that analyze all the like what is modified or something. It just shows what block has been modified. So you can just do your more research and you can find what has been changed. Actually, Yeah, this one actually has been like some researcher actually did binary diffing for this same vulnerability just same day when the patch was out, and they made exploit, working exploit the same day, I think. Same day or the next day maybe. So this one is real one. So, okay, let's back to the presentation. So you now have the idea of what the binary diffing is. Let me check. Okay. Okay, let's talk about the history of binary diffing. This is very interesting because the first binary differ article was like released 10 years ago. Actually, it's from Microsoft. They were using this for like doing performance data transfer or something. And I read the paper, yeah, but second one was Halvar. Actually, he released the bindiff. It's a kind of expensive, more than $1,000 commercial tool. And actually, it's not affordable to the non-corporate researchers. And Todd also wrote some article about binary diffing like 5 years ago. And EI, actually this is the company that I'm working for. The EI released EI binary diffing suite like in 2006. And there are also 2 or 3 free or open source tools available. So there are a lot of tools that you can use, actually, not only my tool. So let's look deep into what they were doing. Like BMAT, it was back in 1999, yeah, exactly 10 years ago. They were using, mainly was using like a symbolic name matching because they were like Microsoft researchers. They could access all the Microsoft symbols, so they could use that. And they were also using 64-bit hashing-based comparison for the blocks inside each procedure. The hashing is based on the instructions and opcode and operand or something. And there are like 4 different levels of abstraction level or something. And after that, 5 years later, there was a Black Hat talk in 2004 by Halvar. I'm not sure the name is Halvar or something. I'm just assume that it's Halvar. Yeah, Halvar gave a talk about just reverse engineering, and a few slides contained some material about the binary diffing, and it was using signature of functions. And the signature of functions was got from the number of nodes and number of edges and number of calls of that function. So if the numbers are same, you can just think that the functions are same. So, and they are also doing like isomorphic comparison between functions, call graph, and so they just think that function as a node and a call as a edge, and just match this through the isomorphism. So just after that, like Todd Sabin made an article, and it was using like graphs isomorphic matching. But the very interesting thing about this is that it was using instructions as a node, not the basic blocks. So it is very unique and yeah, maybe very effective or something. But there were no POC ever released, and they were only releasing like some testing chart or something, and that was all. And after that, there was a more improved version of Halvar's talk, and it was structural comparison of executable object. And after that, he made a new improvement, like with new paper. Actually, yeah, they are basically same. They are using mainly dependent on call graph, control flow graph and call graph. And let's talk about the tool. Halvar actually released bindiff in 2004, like 5 years ago, and it's a commercial one, and based on his graph-based functions, fingerprinting or signaturing theory. And there is IDA compare, it's from 2005, and it's also based on signature scanning. So I'm not sure what it's using because it's not open source. I'm not sure what it is using, but sounds very similar to that of Halvar's. And it was mainly used for malware research, like a malware analysis, data transfer or something. And they were designed for around 500K file in size, and which is very small because like a binary, the Microsoft files are usually like 800K or 1 megabyte or 2 megabytes or something. So this is not suitable for like dipping Microsoft patches. So in 2006, EI binary dipping suit, and it was especially made for like a Microsoft patches because we are like a Windows security company. So we were like looking into whole Microsoft patches. And at that time, actually, they were like doing like a manual binary dipping. Actually, it's possible. Many people will think that it's not possible, but all the researchers in EI were like doing the binary dipping, like opening up two IDA windows and like comparing them manually, and like it worked actually. They found the patches very well, and I made a tool because I couldn't do that. So, and there were new tools like 2008 patch diff 2, and this was specifically made for security patches or hotfix. So maybe you can use this tool. This one might be very effective for like analyzing the Microsoft patches or Sun or Adobe patches. But looks like they are using very similar algorithm to that of Halvar's bindiff. And Darangrim 2, actually, this is using same algorithm as that of EI binary dipping suit, but it's improved version. Like old version was using Python, and it was using a lot of memory, and it was very slow. And I just ported all the code to C++. And actually, it's not open source yet, and we are going to open source the code in few weeks. So let's talk about the algorithm. What is different? What is the difference between Darangrim and like other like bindiffing tools? Actually, previous works mainly concentrated on the graph isomorphism, like CFG or CG that is generated by IDA, but we are mainly using basic block fingerprint hash map, and we are using it to like overcome the problem with the CFG. And this is very simple, actually. You can just generate a fingerprint of the basic block from the instruction set, instruction sequences. You can just extract the instruction sequences, and you just take out some useless information like offset or something. It can be like a changed for each compilation or something. You can just ignore that kind of information, and you can make a fingerprint out of basic blocks. And you can make a hash map out of it, and you can just compare them between binaries, original and patched binary, and you can find the matched one, then they are same basic block. And actually, we are using IDA for like generating fingerprint hash map. And there are some issues like order dependency. We will talk about this later. And there are like hash collision. Like if basic block is too small, then the basic block can be like have collisions. There can be same basic blocks in same binaries. So to overcome that, we can merge multiple fingerprints from parent and children nodes and make it more unique. And to determine matching functions, we just count the numbers that each function has matches, and we can choose the function matches that has the highest number of matching basic blocks. It's very simple algorithm. And we are also using like a symbolic names matching, of course. It's very effective way, like especially for Microsoft patches, because they are releasing like symbol files as soon as they release patches. So when you download the patches, you already have the symbols on the symbol server. And we also do the structure-based analysis. It has some philosophy of divide and conquer. It is very similar to like a BMAT to like 10 years ago. And we use fingerprint to calculate match rate, and we are using like a same string match algorithm that is used in GNU diff. And we just determine whether stop or go based on the match rate. If the match rate is like 80%, more than 80% or something, we can just go. Or if smaller than 80%, we can just stop there, and we will not do the structure-based analysis anymore or something. And there is some issues like control flow inversion. It is already like presented by Todd's article, and like we are also taking care of that. And we will talk about the real life issues like split blocks. Actually, if you this is from some Microsoft patches, and looks like actually the yellow block means the block has been modified, and the red block means the block is not identified because of the yellow block is like blocking all the further analysis. And if you look into more like left and right, you can see that here, this part, here is just jump instruction. It's just going here. So maybe you can just merge them. And if you merge them, then the result will be like this. And they will recognize as the same, and we will do more structure-based analysis, and all the red blocks became like white blocks, which is like a matched one. And second issue, there is a hard patching issue. There is a hard patching preamble or something in Microsoft patches or Microsoft binaries, but there are sometimes the older binary didn't have it, and sometimes newer binary have it, or vice versa. So in that case, that one instruction, move EAX can break whole like a fingerprint match or like a just basic block match. So we can just ignore that kind of pattern. It's a very simple pattern. It always happens at the start of function, and it's always like move register A to register A, which is doing nothing. So we just ignore that. And the third issue is very interesting because like one basic blocks actually can be member of multiple functions. This is very interesting because IDA can't make one basic block be member of multiple functions. So IDA must choose one function, like if each member of multiple functions, it must choose one of them. So maybe it can lose some, like, it can fail in like identifying some functions in during the time. So because that's the limitation of IDA, And it usually happens with Windows kernel because Windows kernels like need to save the space. They are they are doing severe optimization and they are reusing some basic blocks from other functions if they are same. So we are doing our own CFG analysis again because IDA can't handle multiple functions for a basic block, one basic block. And there is issues like instruction reordering. It is very interesting because it happened during we were doing iPhone binary diffing, experiment or something. And we found that they are doing we did a 2.2 and 3.0 firmware kernel diffing. And looks like with new firmware, they did a lot of instruction reordering, and it made our tool fail because the instruction sequence is different and we rely on that sequence. So yeah, this is the example. Actually, left and right block looks very similar, but if you look into more, the colored one, blue or red and yellow lines, actually they are out of order on the right and left. They are not matching. So we solved this problem just generating data flow graph and serialize each node and reordering by reordering. The old one becomes a left one. So yeah, they match. So examples. So about the gathering binaries, actually I usually do the MS patches diffing. Yeah, MS patch is always available on their page. Yeah, it looks like there are some problem with the projector, but yeah, maybe you can read this, still read this. So yeah, so there is MS patches, you can download them anytime you want. And there are some other vendors like Adobe or Sun, and if they release patch, they will withdraw the old binaries. In that case, you can't download the files on the web. So you need to archive all the binaries on your machine before the patches comes out. So maybe you can prepare the future patches. So I made a tool a short executables.exe. It's just retrieve version information from each binary P file and just copy them to specific archive directory using company name, file name, and version name. Here's the example for MS HTML. Each under Windows XP, Microsoft Corporation, this is company name, and under MS HTML. And there is multiple versions of binaries here, 6.0, a lot of 6.0s that I collected from a lot of machines. And there is 7.0 and 8.0. So you prepare this archive, and whenever the patches comes out, you just compare with one of them, anyone that is closed. And performing diffing, it's very easy. You just run darangrim2.exe and open 2 IDA sessions and just run the darangrim2 plugin from each IDA sessions, and it will send the data to darangrim2.exe, and it will do all the job for you, and you just need to check the result. Or you can just use darangrim2c.exe, which is a command line tool that I used for the demo. And it's handy, batchable, and quick, and you can just put the file name, and it will do all the jobs in background, so you can use some Python script to run this tool. Oh. So this one is that actually we saw from the demo. and MS-08-06-7, which was exploited by configure1. This is a RPC vulnerability, and it is very hard to find this bug actually using fudging or static analysis. It's very hard to find this bug. But using like after the patches comes out, the binary diffing takes only 5 minutes or something, and you can just pinpoint which function had the problem. And yeah, this is same graph you saw. Like all the red blocks, you can just need to look into that. And the second example is MS-08-063. Actually, this one shows a lot about the difference between Darangrim 2 and bindiff. This page shows the result from Darangrim 2, and it shows 7 functions have been like modified. From one of them, there is SRV issue query, directory request, and you can see that left one is like unpatched, and right one is patched one. And left one block becomes like split into like 4 blocks. Looks like they added a new check for something. So you can look into more. This one block becomes like 4 blocks, and you can close up. You can see that they are doing some kind of comparison here, RTL, Ulong, sub or something. Here again, they are doing twice. And maybe you can just trace which variable they are like comparing, and you can just pinpoint which like a parameter or packet was causing the issue. Actually, this is from the bindiff help file. They were using this example as their like instructions. So this one is patched, and this one is unpatched in their case. And if you look into that, they are showing same result. So basically, bindiff and Darangrim 2 are showing same result here. But the difference is here, like they only listed 3 functions modified, and Darangrim 2 showed 7. So like Darangrim 2 is more verbose. Like it shows a lot of results that might not be interested to the researchers. But like bindiff can lose some results. They can have some false negatives. And there is also a wrapped up case. There was 0-day out there, like, and exploits out there. So there is no meaning for like a binary diffing this kind of patches, but you can still learn something from what Microsoft is doing. So if you diff MS-09020, there is a function that is changed here. It's about some Unicode conversion or wide character conversion function. And the original one, and this is patched one. The problem is that they look almost same. Because there is no red block, it means that they didn't put any like a logic check or comparison or something. They didn't put that, just changes something here. So we look into more. The original one was like when calling multi-byte to wide character, like converting multi-byte to the wide character string, they were using like a flags from some function result, and they were doing some kind of arithmetics here. But patched one, they are just simply putting 8 here. So they are doing something here. So we can just look up the manual page, the MSDN for this API. Here, I just copied it here. MSDN declares that like following. The flag A means MB error invalid characters or something. So you can just read here. If this flag is not set, the function silently drops illegal code points. It means that even though you pass some invalid Unicode characters to the URL, it will still process other valid parts. So the filter looks into the original request or something, and it sees that it goes through the filter, but it still succeeds with the Unicode conversion, and it goes through the filter or something. So yeah, this is a very interesting case. Actually, if you look into their like a securing code or something, the book has this example, like a similar example in their book, and it's from Microsoft, and like they looks like they failed to identify this issue. And the original binary actually was using like here is UTF-8 or something. It was doing like some heuristics to determine whether it's a UTF-8 like a characters or something. And it was doing some arithmetics here. So anyway, sometimes it fails to identify UTF-8 and like passing some invalid flag for the the API. And next one is not MS1, the Sun JRE font manager overflow. I remember this one was out like a few months ago, and 2 or 3 months ago. And it was actually, it took more time than Microsoft because they patched a lot of things. So it took like, not 5 minutes, it took like 1 hour actually to pinpoint this point. And here, left block, the yellow blocks became like splitted. They put new red blocks here. So look closely. And if you look into here, they are calling malloc here, like for allocating memory. Actually, they are checking something here, like if the length for malloc is greater than some value, big value, they will just fail. So looks like they are doing something good, but they are patching here. What are they patching? Actually, from the disassembly here, if you look into closely, they are adding some original data, and they are adding some value like 0.08 to that, and they are comparing that result to that big value. So if you pass like a big value for the original data length, then it can overflow the integer to make some very small value, and you can pass that check here. So in that case, you can cause some kind of integer overflow. So they are patching it here. So you can just know that they are patching integer overflow here. So, and you can just like trace back the variable that is they are checking, and you can just determine what was causing the problem. So yeah, here's some more interesting one, like 4th of July DDoS attack. I believe that nobody here might have heard about this because it didn't have any impact on the US network. Actually, it was like 4th of July, actually this 2009, 4th of July, somebody made a DDoS attack on like against US government and some corporate sites like NASDAQ or something. And actually, it had a very limited impact against the targets, like just 1 or 2 websites were down, but nobody noticed because they never connect to that site. But for some reason, they changed their target to South Korea. I'm not so sure why they did that. Somebody said that it's from like North Korea or something, but I'm not so sure. And they changed their target to South Korean government and major news sites. And this time it made a huge success, and like the targets were like almost unreachable for like 3 days. And during the time, there were a few variants of the malware samples and collected. And one of my friends sent the samples to me, like, and I analyzed 2 of them. And here's the result. The difference happened only in this part, like from left and from to right. So they added new routines here. The yellow blocks are almost same, so you can just ignore that. So what they did add, actually, if you look into here more, they are like doing some kind of file operation, like from its own binary, it's like retrieving some target list, new target list, and saving it to the target list file. So with binary diffing, you can just retrieve the new information from the new binaries, and you can save a lot of time for like a malware analysis. If you already have done the, if you already have finished the malware analysis for the original binary, you can save a lot of time to analyze a new binary because you can just need to look into the changed part. So yeah, it's about anti-binary diffing. If you look into the white paper on the CD-ROM, I described a lot about all the techniques here. So I thought about, yeah, the simplest one is like a symbol mangling, like when MS releases patches, maybe they can change the name slightly, like to circumvent binary differs. It will make a lot of problem for some binary differs. And maybe you can just reorder or replace instructions like from like XOR EAX to like a move EAX 0 or something. You can just replace some instructions and or reorder, just like iPhone binaries. And or you can just do CFG altering, like a control flow graph altering. You can just put some null basic blocks between the control flow, and maybe you can share some basic blocks like just Windows kernel, or you can just use multiple fake heads for a function, or you can do the CG altering. Use proxy call like doing nothing but just calling the original function. You can just replace it with the original one. So there is a new tool, like anti-binary diffing tool, Hondon. Actually means chaos. And actually it's not doing the extensive code obfuscation at all, but it's doing very slight like code obfuscation by just putting some meaningless blocks between the call graph, control flow graph. So it's implementing CFG altering. Yeah, it's not doing like a symbol name mangling or something. It's only doing like CFG altering. And actually, during the test, I was surprised because I did some like CFG altering, and it broke IDA a lot. So I need to like make it more slight so that IDA can like at least like recognize some functions. And it was tested under 5.0 and 5.5, and 5.0 is broken totally. And 5.5 is much better, but it's still breaking, like it's still confused about some functions. And yeah, ironically, Hondon works as an IDA plugin. So, but in real world, maybe they can like put new flag for like Visual C++ or GCC options or something. I'm not sure they will do that, but yeah. And Hondon is using binary rewriting technique to generate the obfuscated binary. So demo, yeah, there is a very simple demo. Actually, let me check. Here's the Hondon directory. If you look into here, here's this is IDS script. IDS script. It's simple, just wait and run the plugin. The plugin name is Hondon. And passing some parameters and run Hondon. This is the internal function inside Hondon. So it's run and pass the original binary and output binary as the parameters. And it just runs Hondon. And test, this is a batch script, just running IDA and it's calling the IDC script that I just showed. It will run this script here from this binary, or this batch file. So I will run the script here. It was test. Yeah. So it's running and it analyzes the binary and it's creating new binary and opening that binary that is created. Actually, it's not like a completed yet, so it makes some problems to the IDA, but it's okay to show the concept. It's analyzing the binary. You must look into this. Like it's still doing the analysis here, but like originally this binary had like more than at least 100 functions, but it becomes 3 because it's confused on the like CFG. And let me show the original binary. This is the original one. Right. Here's the functions that the original binary had. Like it had a lot of functions, but after running Hondon, it only recognizes 3. The problem is actually I added these instructions here at the start of each function. Like it's doing nothing, like add ESP0 and J and Z, so like it's always true or something. If I put like a JMP or something, the IDA is more like confused, so I just did it for the demo. So if you go there, it's very confused. Like it goes here, and it actually these instructions are from the original function. I just copied it here, and it's going to the original function. But the problem is that the later part, actually this is from other function. Actually, I did it for every function, so I'm just copying it to the end of the section. So this is from other function, but they either still recognize this as the block of the former one. So like this is a kind of a chunked basic blocks, and IDA had a lot of problems. Like traditionally, it had a lot of problems in recognizing chunked blocks. So it still had a lot of problems, and the Hondon is like exploiting that problem, like creating a lot of chunks, and it fails. So actually, let's back to the presentation. Okay. Yeah, conclusion. Actually, if because the tools are maybe IDA can like their improvement on the chunked function recognition, but maybe at that time maybe we can make more like more aggressive obfuscation against that. And there is a conclusion here. the one-day exploit threat is real, and actually it's happening. Like in 2008, I saw a few cases with like one-day exploits floating around, and someone find the vulnerabilities fixed silently. Yeah, Microsoft does that usually many times. You can find a lot of interesting stuff inside the Microsoft patches. And bugs tend to aggregate, and many times around where bugs were found, there is also some other bugs, or maybe, and sometimes they fail to fix the problem. If you have information on the patch itself, maybe you can check whether they apply the proper like a patch or something, and maybe you can find the 0-day out of one-day exploit or something. So yeah, actually there are some cases like that. And Hondon attacks binary differs weak points. The weak point is that binary differs, all the binary differs that I know depends on IDA. And IDA is like very poor in recognizing chunked functions, and Hondon is attacking that. Okay, yeah, that's it. Yeah, thank you.